Matter is made up of atoms. Atoms have three fundamental particles, right? Protons, neutrons, and electrons. Essentially, all of the mass of an atom is in the nucleus, which is protons, which are positively charged, and neutrons, which are neutral. The electrons have essentially no mass. The number of protons is the thing that defines an element, right? So, for example, carbon, what makes an atom a carbon atom? Well, it's that it has 6 protons, all right? The number of neutrons can change, and when we have a variable number of different numbers of neutrons, the relationship is that these are isotopes. So, for example, carbon, most of the carbon in the universe is carbon-12, so 6 protons and 6 neutrons. There is some that is carbon-13, 6 protons, 7 neutrons, and an even smaller amount, which is carbon-14, 6 protons and 8 neutrons. If you have a different number of neutrons, you're a different element. A different number of protons, then you're a different element. Okay, so when you're reading the periodic table, again, this is just a refresher. It's presented different ways, but often like this, where you have the symbol, then you have the mass number, right, which is the mass is the protons and neutrons combined, and then you have the atomic number, which is the number of protons. So remember, an ion is an atom that has either gained or lost an electron. If something has lost an electron, it becomes positively charged. It's called a cation. And if something gains an electron, it's an anion, and it's negatively charged. Typically, metals become cations, and non-metals accept electrons and become anions. We'll talk about more of that a little later on. So this is just a reminder, because there are still some confusion often. So this is chemistry of solutions, which means that we're really going to be dealing with chemical reactions that happen, well, in solutions. So the fundamental thing that we need to look at to get started is, 1, what does it mean when something is in solution? And 2, how do we count how much stuff we've got? All right. So there are a few different ways in which this can happen. So in general, we classify compounds into 2 broad categories. We either have ionic compounds and covalent compounds. So ionic compounds are compounds that have generally a metal and a non-metal, right? So sodium chloride, for example. And they're held together by what we call electrostatic interaction. So you have a positive charge and a negative charge, and they're attracted to each other, right? There are no actual molecules of ionic compounds. So if I have solid table salt, for example, sodium chloride, you can see that in purple, those are sodium ions, and in green, those are chloride ions, Cl minus. And none of these really attracted or connected to one other one in particular. They're all surrounded by each other. In contrast, covalent compounds have actual chemical bonds. So for example, in water, you have, say, this hydrogen that is bonded only to this oxygen. And they're held, the whole big bulk thing is held together by what we call intermolecular forces, which we will deal with next semester. Now, the thing is, the way these 2 categories of compounds behave when they dissolve is different, all right? So basically, if I have my solute, the thing being dissolved, and then I have my solvent, like water, for most of what we're going to be doing, they need to sort of interact with each other in new ways when dissolving happens, all right? And we're mostly, for this course, interested in water for the main reason that water is common, all right? Water dissolves lots of different things, mostly because it's polar. And when we talk about something being polar, what that really means is that the electrons in the molecule aren't evenly shared or evenly distributed. So one end of the water molecule here is, this is where the oxygen is. This has a partial negative charge on it. So this symbol here, this is a lowercase delta, the Greek letter delta, and we use it to denote partial. So the delta minus, what that means is that it's a partially negative charge. It's not a full negative charge. It's negative-ish. And this end of the molecule here, where we have the hydrogen atoms, that is end is partially positive. So why is this interesting? When ionic compounds dissolve in water, the ions actually separate from each other, right? So if I have just table salt, where the sodium ions and the chloride ions are attracted to each other, when it goes into water, water molecules surround each of the ions, all right? And the reason water does such a good job is because it has one end that's negative and one end that's positive. So when the sodium ions are being dissolved, what happens is the negative end of the water molecule points towards the sodium ion. When the chloride ion is being dissolved, the positive end of the water molecule surrounds the chloride ion so that they get solvated. So solvation, or because it's water, we call it hydration, just means that the particles are completely surrounded by the solvent. So you can see here, for example, I have a sodium ion and it's completely surrounded by water molecules with the oxygen pointed toward it. And then the opposite is true here. Now, it's really important that when we have, say, sodium chloride dissolved in water, there isn't actually any sodium chloride, right? We have sodium ions in water and chloride ions in water, not actually sodium chloride. We often write it as a shorthand, but you have to remember that it's a shorthand. So let's see if I can mark this up. I sometimes can, I sometimes can't. So, for example, like if you have in the lab a bottle of salt water of aqueous sodium chloride, you might see it written as NaCl AQ, right? But it's important to recognize that what this really means, so it's a shorthand for the fact that we have sodium ions that are dissolved in water and chloride, and chloride ions dissolved in water, right? This is more realistic. Okay. Now, this is in contrast to what happens with a covalent compound in water. So let's take, this is sucrose, so sugar. Now, covalent compounds, when they're held together by covalent bonds, and when they dissolve, the actual molecule stays together. They just get separated from other molecules. The actual chemical bonds don't get broken. So when I dissolve sugar in water, I still actually have sugar molecules. I don't have carbon, hydrogen, and oxygen atoms in water, all right? So what happens is the sugar molecule gets surrounded by water, but the atoms actually stay connected to each other. So there's a big difference. Sugar, C12H22O11 aqueous, right? So this and this, in the terms of how we write them, they look the same, right? But they mean different things because they are different categories of compounds, right? In the case of the sugar, which is a covalent compound, right? Well, this is what it really means. It means I have sugar molecules surrounded by water. In the case of an ionic compound like sodium chloride, the reality is this is a shorthand for this. All right. So because of the type of compound that we're dealing with, different meanings for things that that look really similar to each other. So we have to watch out for that. All right, electrolytes. So electrolytes really are solutions that conduct electricity, right? Outside of chemistry class, we mostly hear about these in terms of sport drinks. And so really Electrolytes, a drink with electrolytes means really just that it's salty. The thing is that solutions that have ions in them conduct electricity. And we're going to spend more time talking about this a little later in the semester. But so if we have an ionic compound dissolved in water, like sodium chloride, then it's going to conduct electricity very well. So the light bulb's pretty bright. A weak electrolyte is a solution typically of a weak acid or a weak base. So the picture in the middle here, that's vinegar, acetic acid, which is a weak acid. And we are going to talk about weak acids later on in the semester. Those, because they only have a very few ions in solution, they conduct electricity only a little bit. So you can see the light bulb is pretty dim. And here, when you have covalent compounds in solution, they are non-electrolytes and they don't conduct electricity at all. All right, so just when we talk about electrolytes, you need to, just so we know what we're talking about, is solutions that conduct electricity. The last one, this is where practice is better than anything else, but the measures of concentration. All right, so concentration just means how much stuff is there in the solution, how much is dissolved. The most common measure of concentration that we're going to use is molarity, right? So the number of moles of solute per liter of solution. Another common one is, oh, there's a mistake in this. It should be kilograms of solvent. But molality is moles of solute per kilogram of solvent. We'll talk about that in a little later. It's almost never used, but there are a few cases where molality is important. And then outside of the lab, percent mass or percent volume are often used a lot of the case. So if you look, for example, at like a bottle of wine or something, and it'll say 13% alcohol by volume, right? And so what does that mean? It means that there's 13 milliliters of ethanol in 100 milliliters of the wine, all right?